In this example, we're going to look at a firefighter on a ladder. And we're going to analyze that configuration for static equilibrium. All right, and I'll go ahead and read the problem on this slide that says a firefighter on a ladder. It says you have an 8-meter ladder of weight 355 newtons leaning against a smooth vertical wall. So let's start to draw some of this as we go. Okay. Well, we have this ladder, all right, leaning up against here. Okay, and it tells us that that is 50 degrees. Okay, and we also have this firefighter right there. Okay. Next, it says the term smooth means that the wall can exert only a normal force, right? So this guy leaning against the wall, that means that there's going to be a normal force pushing back on it of force N, right? But there's going to be no friction. So there's no friction up or down here. There's just that normal force. In the slide, they use the variable P. I'm not sure why. I'm just going to use N because it just makes more sense to say normal force, right? So the firefighter who has a weight of 875, alert, they're telling us more information. So this is, we have a firefighter applying a force to the weight firefighter, which is 875. Okay. And they're standing 6.3 meters up from the bottom of the ladder. Okay, so this distance here is 6.3. All right. What else do they tell us? Assume that the ladder's weight acts at the ladder's center, right? So if the whole ladder is 8 meters, then we have the weight of the ladder which they tell us is 355, that must be acting at 4 meters. Okay? And the question is, find the forces that the wall and the ground exert on the ladder. Okay, the wall and the ground exert on the ladder. So this normal force is the force that the wall exerts on the ladder here. But at the ground, there's going to be a second normal force, right? And it's kind of hard because I have all this other stuff here. But I'm going to make room for it. And I'll call this ground Y, right? Which is the force that the ground pushes in the Y direction. And then I'm going to call this here ground X, which is basically the frictional force that the ground applies on the ladder so that the ladder doesn't slide out, right? So really in this problem, we're trying to find GY, GX, right? The components of the force that the ground applies on this ladder in the Y direction and in the X direction, and we want to find N. Okay? This is, as you can see, a little bit more complicated. And in addition, we now have these angles, right? This is a 50-degree angle, which, by the way, is going to make that 40 degrees and that 40 degrees. That makes life a little bit more complicated too, right? All right. So what do we do here? What do we do? Well, we do exactly what we did before, but now when we write our equations for the conditions of static equilibrium, we need to make sure that we have the sum of forces in X, all right? Because that exists this time. So I'm going to say sum of forces in X must equal 0, right? But what are the forces in X? Well, I have a positive X force, right, GX over here, right, pointing this way. And then I have a negative X force pointing this way, which is this N, right? So we know that whatever the friction is, right, here, applied here, must be the same as whatever the normal force of the wall pushing on this ladder must be. So Gx minus N equals 0. This tells us that Gx equals N. Helpful, but not super helpful, because we don't know Gx or N yet. Okay? Presumably, in these other equations, we will get it. Okay, the next condition for static equilibrium is that the forces in y must equal 0, right? Well, what's pushing in the positive y direction? Looks to be only one thing, which is gy, right? And what else do we got going on? Well, we also have a couple of things going in the negative direction, which is basically the weight of the ladder, right? So that's minus 353 newtons. And the weight of the fire person, which is minus 875 newtons. And that all must equal 0. That tells us we can very, very easily calculate gy, right? The force that must be pushing up, and that's 1230. We're 1/3 of the way there. We got one of our three variables that we're looking for. Okay? Lastly, always the beast, always the one I'm least looking forward to, the sum of torques, right? They're always so much more complicated. So the sum of the torques must also equal 0. Okay, what point do we want to pick as our point of rotation? Well, heck yeah, I want to pick that as my point of rotation, because if I do that, two of my torques automatically go away, because R would be 0 for gx and R would be 0 for gy. They cancel out, so I would only have to deal with the two weights in the n, which tells me I would probably be able to solve for n, and if I can solve for n, I can find gx. Okay, did you see that chess that I just did, this physics chess, seeing 3 steps ahead? All right, that's what happens when you've been doing this for a while. So let's do that. So let's start with the positive torques. If I'm saying this is my axis of rotation, what force would cause this ladder to rotate counterclockwise? Well, n, right? If I push on the ladder here and this is fixed, that would be counterclockwise. So the torque due to the normal force, that would be positive, right? And these two would be negative because they would make the ladder want to rotate clockwise. So minus torque of the ladder minus torque of the fire person all equals 0. Torque of the normal guy over here would simply be n times L, which is the length of the whole ladder, which is 8 meters. So 8 times n times sine, what is this angle? Well, we have opposite interior. So if this is 50, that should also be 50. So that'll be sine of 50 minus torque of the weight of the ladder, which is this guy here. Okay, that is going to be 4, right? R is 4 for this. He's 4 away from the axis of rotation. Times, well, we know that the weight of the ladder is 353 times sine of, now that angle there is 40. So this is sine of 40 minus, how far away is the fire person? The fire person's 8.3 away, so that's going to be 6.3 times the weight of the fire person, which is 875, times sine. Again, that angle there is 40 times sine of 40. All equals 0. I hope I'm still on the screen, but if I'm not, we have all these torques equaling 0. This has a value you just put in your calculator. That has a value you just put in your calculator. That has 8 times sine of 50, that has a value, which means solving for n is super, super easy, right? Pause the video if you like, solve for n. Tell me if you get the same thing that I get. I get a value of 205.9, right? And because of this equation over here, gx should also be 205.9. Okay? And now we used basic first semester physics to analyze the stability of a firefighter on a ladder, which basically means that at this point, you guys could either go to medical school or you could become engineers, okay? And build the bridges and the buildings that, we use in our daily lives. Take your pick, either way. All right, that is our last example for this week. I'm kind of exhausted. Hope you guys have a nice weekend.